welcome back to another exciting chemistry video lesson. Today we're going to focus our attention on molecular formulas. In the past, what we did was we looked at the difference between molecular and empirical formulas, and we focused a lot of attention on the empirical formula and how to calculate the empirical formula. So today we're going to turn our attention to the molecular formula. If you remember from the previous videos, and if you need to, go back and rewatch those videos on empirical formulas if you need a refresher or if you haven't watched them. But the big difference was that molecular formulas are used to describe molecular compounds. Because remember, molecular compounds are not always written in their lowest terms possible. So for example, like with this hydrogen peroxide here, H2O2, we actually have two oxygens bonded to two hydrogen atoms. And that's okay because that's how molecules share the electrons. Remember, they can share them in a variety of ways, unlike ionic compounds where things are always written in their lowest simplest whole number ratio. So here we're going to have a mixture of that. So like over here, this is what's called hydrazine. You would have two nitrogens and four hydrogens. So this makes molecular compounds a little bit more challenging to deal with because they can be in quite a variety of patterns. I mean, we could have another one with 3 nitrogens and maybe 8 hydrogens, something like that. Carbons are, have a tremendous amount of combinations that they can follow. So C2H6, C3H whatever. So we're going to look at how do we determine the molecular formulas. Okay, so first thing I want to do is just kind of compare, the empirical to the molecular. So let's say we've calculated an empirical formula. We found that the formula comes out to a ratio of 2:1. So when we deal with molecules, the empirical formula, what it's telling us is the ratio at which those elements are going to be found with each other. So for every 1 carbon, I have 2 hydrogens. That's what the empirical formula could tell me. I might have a formula that is maybe 1 carbon to 3 hydrogens or 2 carbons to maybe 5 hydrogens. Probably not likely, but again, it's just showing us the lowest whole number ratio. That is the goal of the empirical formula. So what if our molecular formula actually was C2H4? Well, notice what's happening here. It's staying within that ratio, that 1:2 ratio that our empirical formula tells us, but it's going up by some kind of multiple. In this case, it's going up by a multiple of 2. So therefore, if we were to look at this and actually calculate the mass here, so let's just do some quick rough estimate, measurements with the masses here. So we get this out of the way. So let's say we take this carbon, which has a mass of 12. I'm just roughly rounding these numbers, nothing specific here, just to show you the example. And each hydrogen is 2. So that's going to give me a mass of 14 grams per mole for that molar mass. So if I know that my formula is twice as many carbons and twice as many hydrogens, wouldn't it make sense that my formula mass would be twice as massive, right? My molar mass would be twice the mass of the empirical formula, right? So therefore, if it were 3 times as much, then my formula would be C3H6, and therefore this would be 3 times as great, which would give us 42 grams per mole. So what we find is if we know the empirical formula of this compound that we're dealing with, we know that it has to, whatever the molecular formula truly is, because remember, that's what it does. It shows us the actual ratio or the actual elements that are in the compound, has to be some kind of multiple keeping that same ratio intact. So what if we had a molar mass of 126? What if we were able to figure out through experiment that the actual molar mass of this compound comes out to 126 grams per mole? Well, if we were to look at that, we could figure out what the ratio is between our empirical formula. If we know that this is the empirical formula, we could then figure out what our formula, or I should say our molecular formula actually is going to be. I could figure out what X and Y are. So if I start with the 126, I'm going to use this little calculation here, which would be the molar mass of the substance, which would be this number here, which whatever the substance happens to be, its actual true molar mass. And we would compare that to the molar mass of the empirical formula. So what I would do is I would take 126 and I would divide that by 14. And when I do that, I'm going to find that that is 9 times greater. This mass is 9 times greater than the mass up here. So therefore I can conclude, based on the fact that I see this pattern going on, that this formula has to be 9 times greater than the formula of the empirical formula. So therefore I'd have C9H18. And that's really the trick that I'm going to use to figure out my molecular formula. So really, molecular formula problems are nothing more than empirical formula problems with just one more step added to them. So let's take a look at another example. Okay, in this example we have a compound used in rocket engines. It has an empirical formula of NO2. So we know that whatever this compound is has the ratio. Okay, so we're looking for what the actual formula is. But we know that the empirical formula is going to have a ratio of 1 nitrogen to 2 oxygens. So this formula could be N2O4, N3O6, very similar to that carbon-hydrogen one I just did. So if the molar mass of the fuel is 92, so this is the actual molar mass of the fuel that they figured out. What is the empirical formula? Well, we're going to go back and use that comparison. We're going to compare this molar mass to the molar mass of my empirical formula. So the first step is to calculate the molar mass. So we have nitrogen, which is going to have a mass of 14.01 grams for every 1 mole, and oxygen, which is each of those are 16 for a total of 32. So my total molar mass here is going to be 46.01 grams for the empirical formula. So what I want to do is compare that to the 92. So I want to see how much greater 92 is than the 46. So we do 92 over 46.01, and we can kind of compare these two and see which is greater, or how much greater the 92 is. We know that 92 is greater. And we end up with something like 1.999, which is essentially 2. So we can see that the molar mass of the actual formula is twice the molar mass of my empirical formula. So therefore, what I can do is I can say that the actual formula is twice the nitrogen dioxide. So therefore, it's going to be N2O4. And there you have it. That's how you would do it if you know the empirical formula. Okay, so what I'm going to do now is I'm going to do a problem from scratch. So this is without knowing anything about the formula. All you have is just the basic raw data about the elements that are in the compound. So here we're going to determine the molecular formula of a compound that has this percentage of carbon, hydrogen, and oxygen, and they tell us the actual molar mass of the compound. Now I'm going to do this 2 ways. I'm actually going to calculate this traditionally, and then I'll show you a little shortcut you can do if you have percentages and the molar mass like this. Okay, so my first step here is to figure out what the, well, first of all, what am I looking for? I'm looking for this carbon, hydrogen, oxygen compound. I want to know what the formula is for this. This is the goal that I'm looking for. So remember, when I'm looking for chemical formulas, what I want to figure out is how many moles of the carbon, how many moles of the hydrogen, and how many moles of the oxygen that I have in here. So really, I'm looking for the moles of each of these, and I want to compare the ratio of the moles of each to figure out that formula. So what I'm going to do is start with that 48%, and remember, in the previous problems we talked about in a previous video lesson, we talked about how we can use the percentages. So what I'm going to do is assume I have 100 grams, because if I take 48.6 grams of 100, what I'm going to end up with is 48.63 grams of carbon. Okay, so that's what I'm going to do first. I'm going to do that for all 3. Okay, so I've got my masses. Remember, I need to convert these masses to moles. So that's my next step. Convert from the mass to the moles so that I can see how many moles of each I have. Okay, so I've got the moles, and remember when we were doing these problems, we wanted to carry out extra digits so that when we do the next step that we get a little bit more reliable answers, because if we round too early here, we can get a false impression of what the ratios are. So carry out more digits, and we divide by the smallest number, so I'll do that. So here we have our moles of each of the carbon, the hydrogen, and the oxygen. So if you take a look and notice here, I left this as 1.5. Now I know you're told in your math classes that if this is a 0.5, you could round this up to a 2. But if you think about it, that 0.5 is like right smack dab in the middle of our number system between 10 and the 0. So in order for us to figure this out, why would we round up or down? That's just a rule that was made just to make it easier for you guys to round in those classes. This is actually a 1.5 to 3 ratio, or a 1.5 to 1 ratio between the oxygen. I can't lose that ratio. I've got to keep that intact. So what I have to do is a little trick here to get rid of the half. What I'm going to do is I'm going to multiply this by 2. Now, as long as I keep the ratio the same, I'm okay and I'll be fine, so I can get this in a whole number. So I'm going to multiply this by 2. So therefore, what I'm going to end up with is 3 moles of carbon. And down here, I'll get 6 moles of the hydrogen, and I'll get 2 moles of oxygen. So therefore, I've now kept that ratio intact, but now I have these all in whole numbers. So therefore, my empirical formula is C3H6O2. So this would be considered the empirical formula. Now, if you want more details and steps on how I got that empirical formula, you can watch the other video lesson. But what I'm going to do now is I'm going to show you how we take this, and we're going to combine this with the step that we just did for molar mass. So what I do here is I take my molar mass of the empirical formula. I have to calculate that out. And the molar mass of the empirical formula, when you add up all the elements that are in here, is 74.09. So that is the molar mass of the empirical formula. Okay. What I want to do is compare it back to the 222. Notice this is a lot higher in mass than this. If these two masses were the same, then this would be the empirical and the molecular formula. So to find the molecular formula, I just do the 222.29, divide that by 74.09, and I end up with a ratio of about 3. So this mass here is about 3 times greater than this mass here. So therefore, my formula must be 3 times greater than the formula here. So therefore, this formula must be 3 times greater. So I have to multiply this by 3. So therefore, my carbons are going to be 9, my hydrogens will be 18, and my oxygens will be 6. And this will be the molecular formula for this particular compound. Okay? So there you go. That's how you would do the whole thing from scratch, from the percentages all the way through to the molecular formula. Now, if you want to stop here, that's fine, you can, but I'm going to do it one more time, and I'm going to show you another method using percentages. You just watch if you want to see it. Okay, so the second method for doing this is going to focus on using these percentages a little bit differently than I did in the last one. Again, we're still looking for the formula CX, H, Y, oxygen Z, and we already know what it is from the previous step, but it's okay. We're going to try to figure out a new way. So remember we said in the past, in the last problem, what I did was I took the percentage of 100 grams. What I'm going to do now is I'm going to actually take a percentage of the molar mass rather than a percentage of any. Remember, I could take any mass that I want, so 100 works out nice and neat, but if I have the molar mass and I know the percentage, what that is going to tell me is what mass of this is made up of carbon. How much of this 222.29 grams is made up of carbon? Then from there, I can find the moles, and what that will let me do is find the molar mass, the molecular formula directly. So let me show you the example. So I'm going to do the percentage. I'm going to take 0.4863. I'm going to multiply that by the 222.29 grams. Okay, so when I do that, this will give me my mass of carbon. That's 108.0996. Again, keeping more digits just so that the work can come out nice and easy at the end. So I'm not worrying about significant figures yet, because remember, there really aren't any, because these are going to be single whole numbers anyhow. What I want to do is figure out how many moles there are from this. So I do 12 grams for every 1 mole. So just to recap here, this is the mass of this 200. So out of this 222 grams, 108 of it is carbon. Well, how many moles would that be? So I'm going to do this conversion here, and that's going to give me 9 moles of carbon. Now, if you remember in the last step, or in the last example, that was the number of moles of carbon in the overall formula. Now I'm going to repeat this process for hydrogen and oxygen. Okay, so take a look. After doing all those calculations, what I end up with is 9 moles of carbon and 18 moles of hydrogen and 6 moles of oxygen, which is my molecular formula. So by having the information given as it is, where I have the formulas, the percentages and the molar mass of the actual compound, this method will work every single time. Now, if they ask you for the empirical formula, all you would have to simply do is reduce this down. So all you'd want to do here is pull out the 3 from each of these. So it would be C3H6 And that would be your empirical formula for this particular compound, which is what we saw in the previous step. So, two different ways to calculate this. The first method always works. This works only if you're given both the percentages and the molar mass. And you could find the percentages and then do this. It's up to you. There's a lot of different ways to handle it. So hopefully this helps you and gives you some insight into the molecular formulas. Thanks a lot, guys. I'll talk to you soon.